Labvakar! Mani sauc Kaspars Zaltāns, esmu izglītības projektu vadītājs Rīgas Pāles Stradiņa Universitātes anatomijas muzejā. Un šodien ir patiesas prieks jūs sveikt ar mūsu pirmo 2025. gada publisko pasākumu. And as the lecture is given in English, I will switch the language as well, so Gustav can follow. And I don't know, have you been to our exhibition or not, but we are housing a historical collection with more than a century of history. And we are showcasing the physicality of a human body. We are showcasing the so-called normal anatomy, so what you have, what I have, also variations and pathologies, but have about the intangible aspects of being a human. So today with Jurģis Štilters and his team from Latvijas University, and with Gustav Blumberg, this program for the distinguished lectures for cognitive science, we want to showcase these bridges between the human body and the mental aspects of us. And Jurģis will give a little bit introduction about Gustav. I already met him. He's a great spokesperson, and I think everyone will enjoy this lecture. So enjoy.
Thanks, Kaspars. Hi, everyone. It's a great pleasure to see you all here in the Museum of Anatomy. And it's my great pleasure to welcome you to the Robert Blumberg Distinguished Lecture, Cognitive Science 2025. As most of you might know, Robert Blumberg Distinguished Lecture in Cognitive Science was established 2018 in collaboration between the Lab for Perception and Cognitive Systems, University of Latvia, and the Honorary Consul Republic of Latvia, State of Illinois, Robert Blumberg. He was also a honorary member of the University of Latvia, patron, board member of the organization Friends of University of Latvia. And Robert Blumberg Distinguished Lecture in Cognitive Science is the only event in Baltics honoring highest level significant cross-disciplinary contributions to cognitive science. Previous lectures and affiliated events have brought together the most important researchers from the fields like perception, music, psychology, neuroscience, to mention just a few. And support for this lecture, Robert Blumberg funding, is administered by the University of Latvia Foundation. We are also supported, of course, by the Department of Computer Science, University of Latvia, also our co-host Museum of Anatomy, the Student University, and many thanks also to the local team from the lab and museum, and many thanks to Rob Blumberg, the Red Committee, Nora Newcomb, Larry Moss, and Michael Glansberg, who did the hard work to selecting and to filtering out the best of the best. Okay, so we are proud that the Robert Blumberg Distinguished Lecture 2025 is Professor Gustav Gerbeck from Uppsala University, Sweden. And let me say a couple of words about Professor Gerbeck. He's a developmental psychologist who made significant and some groundbreaking discoveries in developmental psychology, but also he elaborated most of the methods that have been used in infants' cognitive, social, emotional development by using eye tracking, by using methods like pupillometry that are very accurate and very important in contemporary research on developmental issues. A particular focus of Professor Gerbeck's research is the analysis of child's active, intentional, and interactional explorations that scaffold development. Another focus of Professor Gerbeck's work is a focus on research growing up in war, parents suffering from mental health problems and societies in transition. And finally, last but not the least, we do think that we are unique in the way we live in this Western, rich, educated, industrial countries. There are also parts of the world that are very different. And there is another focus of what Professor Gerbeck works on, these not Western societies, not industrialized societies. And also, I have to say that if you think about research in human perception, this is my own field, and probably this is a special anchor of today's speaker's contribution that is very important for me, is of course his work on eye tracking and research on pupillometry. So pupil diameter is something that is very informative and crucial when we are examining what's going on in human mind, what's going on in preconscious activity of humans. So this is another very important direction. And Professor Gerbeck is the head of Uppsala Child and Baby Lab, and one of the most significant cognitive scientists and psychologists in Sweden and Scandinavia, and there are numerous studies that have shaped different fields, not just developmental psychology, but also research in human perception. Well, if you think about the perception, then probably the paper on pupillometry is probably entitled Pupillometry Window to the Preconscious. So nobody on this earth who is working on eye tracking can kind of ignore this paper. Then another important study is infant's prediction of people action goals. I think this kind of resonates to what will be also explored in today's talk. And then there are numerous studies on how to apply eye tracking in examining what kids, what babies are doing. And this is another really significant contribution to contemporary science. Also autism research. But these are just a few glimpses into what Gustav Gerbeck has done in the last 20, 30 years. And so now I'm very delighted and honored to give the floor to our speaker, Professor Gustav Gerbeck.
Thank you for that wonderful introduction and for showing the museum, which I agree is amazing. And I'm very happy to be here. I was given a beautiful tour of the city today. I haven't been here before, but I feel like I really want to come back. And thanks to the founder and Robert Blumberg, of course, who are standing behind all of this. I don't have a PowerPoint. I'm just going to talk. That also means that it's totally okay to interrupt me, because I have sort of an idea about what I'm going to talk about, but can easily sort of adjust that to if there are thoughts or suggestions or comments or questions right, along the way. And another interesting thing with doing that is there is no clock. So I've asked you to sort of say that when I should be quiet, because not having a PowerPoint makes it a bit challenging. But it's also more fun, I think. So what I'm going to talk about today, well, that says here how hands shape them. But it's really, I think I'm going to try to convey a story about how young infants start to make sense of the world. How all of us, one time long back, started to sort of decipher the world. And that there are many ways into that, of course. You can start by looking at the social component of the parents and so as teachers who sort of inform a child about how the world is organized. You can think about genetic components to this. And all of these components are true, of course, but what I will focus on is the active, constructive process of the child, where the child is sort of actively taking the lead in trying to figure out how the world works. And then hands are a very good way of sort of a tool to investigate that topic. Okay, so that's sort of what I was going to talk about. Now, I was going to start by saying that, and this is, all scientists say this, so it's a bit hopeless, but I'm just going to say it anyway. Like, in my field, baby science is really difficult. Now, anyone would say perception science is really difficult, and we all feel, probably those of us who work in science, that what we do is particularly difficult. What makes, and of course, you know, being a baby researcher, it's not harder than anything else, but it has some particular types of challenges. Like a classical psychological experiment not having to do with babies, you could be asked to sit in front of a computer for 2 hours and click in certain patterns, given certain very complex instructions, like often done in perception research, for example. or cognitive research. And of course, all of us who've ever met a baby knows that this is completely impossible, right? They don't take instructions. If it's boring, they would absolutely not do it. So what we have to do is find ways of making sure that it's fun and that the babies themselves choose to participate because they pay attention and find it interesting and perhaps even funny or humorous to some extent. But they choose to engage in it. And then we need to find sort of ways of understanding what goes on under the hood of the babies, how they think and how they reflect about the world. Therefore, eye tracking is one out of several ways of doing that. And for those, it's fairly self-explanatory what it is, but it's a camera measuring the eyes of the babies, calculating where they look on a screen or in a live situation. Okay? So I'm going to start off by giving an example of a study, and then I'm going to sort of dive deeper into this and then go back into talk about principles. So let me just explain one typical study, and this happens to be a study that I like quite a lot, that I've been part of, so I sort of enjoy talking about this, so it's a bit of a bias there, but anyway. So you're now babies, okay? You are 1-year-olds. You're looking at either a TV screen or a live interaction between two people. This has been done in several different studies, different ways, but it's always sort of the same thematical structure of this. Okay. I'm the stage, right? Well, I am actually, so it's... In this particular study, there are two people sitting next to each other with a table. And when this study starts, we ask them to talk about whatever they want. And this study was done in Oslo, and they choose to talk about how the psychology program in Oslo was the worst. Not a good way to start a study, but this is what they choose to talk about. So that we let them do that. So they chatter on about how boring it is in school, basically. And then the sort of scripted events. So in these events, after a bit of a conversation, one of these persons says, "I'm really hungry." And then she takes up a plate of banana, puts it on the table and eats it. The other person sitting here goes, "Ooh, that's very tasty. Can I have some bananas?" Of course she can, right? So this person takes bananas and feeds her into her mouth. Again and again and again. 24 times banana is being moved over the table to the other person. And sits there and goes, "Oh, that's amazing. Can I have some more bananas?" Next one, next one, next one. This is why we do it on TV, on movies, because we started doing this live, and the research assistants did not want to do this after a while. Imagine like 24 pieces of banana, then one baby out, next baby in. And then I said, let's exchange bananas for candy instead. That wasn't a good working environment either, so we had to do this on the screen. That worked. So, what we do in this case, as I said, there's this scenario. And we measure the eye movements of these babies. Now, a 1-year-old baby who looks at this, the first part here where the food is being put on the spoon and being brought to the mouth. What the babies do is that they look at the spoon and then look at the mouth before the spoon arrives. So they're anticipating this event. They're actually looking into the future. They're thinking ahead of time. That's what you mentioned as one of these papers. And this is something, when we just do this is something that babies do at a very young age. I'll come back to why, but this is the first description. When the food is being brought over the table like this, actually it's a super weird thing, right? To feed each other with bananas with two animals like this, it makes no sense. But when I did this study, I was going on parental leave with my second daughter, and to me, like, this was absolutely normal. This is what I was doing all the time. And when we asked the parents about this, if this was normal, they're like, yeah, this is totally normal. It's not, right? But imagine there would be a baby there, that would make no sense. In this case, what a 1-year-old baby does, in some cases, is that they look at the spoon and look at the other person before the spoon arrives. But this is a bit more difficult. Like this, for a baby to be able to understand this enough for them to actually look ahead and think about what's going to happen. Keep in mind that there are two people interacting, talking about the psychology program and feeding each other. It's complicated. And for this, this is the first indication why I find this study interesting. It requires a lot of experience for these young babies to understand this, enough to anticipate it. So a 1-year-old baby needs about 200 days of experience of being fed in order to be able to compute this. It's an enormous amount of experience if you're 1-year-old. That's 2/3 of your life that you have to have been fed repeatedly by your parents in a fairly systematic way for you to be able to incorporate that information about your own experience and use it to anticipate someone else. Okay. So if they didn't have that experience, they just track the spoon to the other side like this. But as soon as they start to have a solid understanding of this event, then they start to look ahead in time. This is one part of this. I'll come back to this experience dependency. This is related to this core narrative. But this is an experiment, right? So we have another condition where we do something else, otherwise it makes no sense. So in this case, it's the same two people sitting around the table talking about how crappy school is. One brings up bananas, starts to eat, the other one says, "Oh, I'm so hungry, can I have some?" Sure. But instead of the spoon going to the mouth, it goes to the back of her hand, and then she goes, "Wow, that was amazing, can I have some more?" The bananas goes here, 24 times again. They didn't enjoy that either, the assistants. But in that situation, what happens then? Well, these are new kids or the same kids on different locations. We've done this many times. So when this happens, of course, they anticipate. When the spoon goes over the table, those that have a lot of experience, they look at the mouth every time. Like 24 times in a row we do like this, but they never learn from TV in this case. They seem to always go back to their own experience. What should happen now, given what I have experience with? What makes sense to me, given my prior history? And then they look at the mouth ahead of time. And those that don't have experience keep tracking the spoon, but the anticipation goes to the mouth. What really happens then is the most interesting thing, I think, in the long run, because the kids get surprised. And that's what we can see with pupil dilation. This was actually the first study we used pupil dilation. Because what happens then is that the spoon goes to the back of the hand, the babies look to the mouth, and when they realize that this is not right, their pupils become enormous. And what that means to me is that it's a bit unclear exactly what it means, but it's something in between surprise and arousal. I think we'd like it, that's sort of what we're capturing. And then the spoon goes back, the next time again, the pupils become really big. And then when the spoon goes back, they relax again. 24 times. Again, they never sort of seem to learn from it. They always seem to draw from something else, their past experience of these things. Another twist to this that became interesting is that these are I talk about the neuro 1-year-olds. What about 6-month-olds, for example? Well, 6-month-olds do not have that massive amount of experience of this type of action. They do with putting things in their mouth, because they do that all the time. So they can still anticipate this. But when the spoon goes over the table, none of the 6-month-olds could anticipate this. But what was so surprising is that they were still surprised. To the same degree. No, it's good. The same with 4-month-olds. We haven't done younger. But we just keep the youngest we get, they still become surprised. Now, it seems from this study that in order to anticipate something, you do need that massive experience of that. So that comes from your life. But these 4-month-olds, they had very, very little experience being fed, and they still become surprised. Now, surprise is another form of anticipation. It's a reactive anticipation, but think about when you become surprised. It's because when you think something will happen, and it doesn't happen. So you're sort of forward-leaning in your thinking, and then realize, shit, that didn't happen, something else happened instead. And that results in surprise and these pupil dilations. So even the very youngest babies have some understanding about how this social interaction should happen. Maybe it's bad that I start with this, because this is the big question mark that we still have and the field sort of still struggles with. And this is not only this study, there are multiple from other authors as well, so I'm not pretending to be very unique in this. But the argument is, why do these babies become surprised? Well, here there are two camps. And one idea is that this is that we have a genetic predisposition to understand other people's social interactions. I don't think that makes sense. Like, this is way too complex for that type, for a genetic specification of something like how two people interact while eating bananas. While I was talking about the psychology program in Oslo, that genetic, that's a bit too narrow. Another way to think about this is what we're really measuring here is an assumption that actions should be efficient. They should be rational to some extent. The rationality or efficiency here means basically that if we want food to go to the mouth, we should just put it there. If I should grab my notebook and figure out what I'm going to talk about now, doing it like this is a very stupid way of doing it. And that is something that babies from a very early age have with them, because that's the way they structure their own actions. And we can see that already in the womb, already before birth, when motor behavior is studied with 3D ultrasound, that the way that a fetus towards 2/3 into the pregnancy organize their actions are already then structured in a sort of a meaningful way towards the goal of those actions. So if a fetus but if the fetus ends up putting their thumb in their mouth, that action already early is much differently organized than if they want to touch the binocular cord or touch their eyes, for example. So if the hand goes to the eyes, the movement is smooth and careful already from the beginning, so that the touching is soft. Whereas much more sort of force in the hand already from the beginning, and the thumbs up when it's supposed to go to the mouth, for example. So already from the beginning, when a fetus starts to move, they're organizing their actions in a functional way with respect to some sort of outcome. And that is what I argue is what we can see in the pupil dilation already at 4 months of age. That's an argument, that's not an empirical fact, because that's the question mark, right? What's happening with the very, very youngest. But these are the types of studies we do. And this is sort of the type of work I want to talk about. But going back to what is it that we can see here? So I'm going to talk about a few different examples of areas where we've used this type of paradigm to try to understand and unpack the earliest foundational learning skills of young infants. And if we go back to this with making predictions, so we and others have seen, I think it's around 50 studies right now that have been by many people that have mapped out the relationship between when a child or an infant can anticipate something and their own motor capacities or their experience interacting with others. And through these studies, and it's very systematic, is that there is a clear connection between when a child is able to do something or take part in something that, and when they're able to anticipate other people. So I said before, like, if a young baby sees someone stop putting something in their mouth, this is something that a baby does already before birth, and they're quite proficient motorically to put anything in their mouth. If you just put something in front of them, it's going into their mouth. So if we show a baby those types of scenarios where something is going into the mouth, babies can, from a very, very early age, anticipate that. And that's true for all babies. When we moved further down the line, so if we take another example of a baby that's 1 year old, what they're usually is very occupied with is putting things into other things. So if they have small toys and a bucket, they're very eager to do that. And that's usually because that's sort of interesting for them, it's inspiring, and it's sort of the right level of challenge for them at this point. And then you can see them do this quite a lot. And when an individual child, so if we think of this as multiple children, and we draw a regression line through the motor capacity, so some kids that are 1 year old will be very good at this, and some kids have not yet mastered this. For those kids that just have mastered this ability, they're also able to anticipate other people doing this very action. But a child that has not yet mastered it might need to wait another 2 weeks before they're able to anticipate someone else. We can go into 2-year-olds. Some are really good at solving puzzle tasks, having these simple puzzles for small children where you have a knob that you sort of put the banana in a banana-shaped hole or a pear in a pear-shaped hole. And babies that are good at doing that, kids that are 2 years of age, they're very good at anticipating other people doing the same thing. Now, so there seems to be a very clear link between when you can do something yourself, that's very good for your own motor proficiency and your ability to act on the world. But it also seems to open an understanding of other people and what other people are doing, and gives the children or the infants the ability to read and comprehend other people's actions as well directly, which opens up a window for learning. We can see that this has 2 interesting implications. One is that we are fairly sure what the underlying neural structures are for this. So when we can assess that in different ways, either with infants, we can measure brain activity through EEG and see what types of areas or what type of signal properties that come out of this. And we can also, with adults, something we can't do with babies, is to do functional TMS. So we can actually disturb different parts of the cortex and see what part of the brain are essential in order to make these computations. And the infant work with EEG and the TMS work with adults point to the very same thing. And they suggest that it's your own motor areas that are activated when you observe other people performing actions. So when a child sees someone do something, their own motor system and the motor plans that they have are activated and simulating the outcome of the action they see. And if you have the capacity yourself, you're then able to read other people. So to some extent, through action, you open a window to other people and their internal states. The TMS study we did was one of the scariest studies I was part of, and I wanted to be part of it just because it's, we're manipulating brain activity of other people, so I wanted to be part of it myself. And we went down to Italy to a research group that are really good at that to do this study. And in this study, I was the first participant, and I got to sit down in a sort of an iron cast dental chair. They didn't strap me down, but it felt like this a little bit, super scary. It's because, they should be stable, sit still. And then they have this TMS, I don't know if you know what it is, but it looks like an X-ray at the dentist office. It's like a big white thing like this, that instead of putting it to the teeth, you put it to your brain, to the cortex. You sit very still, and then they put this at a position, and then it's activated. But it sounds like this. And they move it a little bit. They move it a little bit again. And all of a sudden you go, ah, what happened there? Oh, that's the area controlling your arm. Check. That's the super scary stuff. Okay, and then they move it on a little bit further. All of a sudden your leg goes, ching. Okay, cool. That's where your leg is controlled. Actually, I don't know, I say but by law, it doesn't make sense that it's by law, but university policy maybe. So at this university in Italy, there had to be a doctor, actually dressed like a doctor in a white thing, standing, like staring at me, sitting in this chair all the time. And that freaked me out even more. So afterwards, I was like, why was he there? People get so scared by doing this, and they get so nervous that they faint sometimes. And the only reason for this doctor is saying that was not the TMS, that was you being scared. That was the thing that guy was doing there. Didn't help at all. Okay, so now we've established that there are two parts of my brain, of my motor cortex, that controls my arm and my leg. And what I was watching then, and other people in the study as well, was basically a hand reaching for objects. Same things that we showed to babies. I know how to manipulate objects with my hands, so when I look at this, I will anticipate these things, right? But if the TMS activated like 200 milliseconds after the hand started to move on the screen, and the TMS was over the motor area controlling my arm, the ability to make predictions about other people was vastly diminished. But not when it was over the leg area. And then there's also this scan condition where it sounds like it's activated, but it's actually not. So you have a proof, but nothing actually happens. So you think it's being manipulated, you think that your brain is being activated, but it's not. And then you didn't find this effect either. So that's like a causal evidence in adults that our own motor cortex is involved in understanding other people. And that's the same thing I argue happens with babies, though there we have correlational evidence, because TMS with babies, I don't think it's a good idea. I don't want to do those things. So that's one thing. So I think we know what's happening, and it's fairly clear that for this ability, having a lot of experience participating and doing helps understanding other people. And the more we grow motorically, the more we understand other people. Why this is also interesting is that we see a very clear link in this direction. We see the link between if you can perform the action and if you have experience doing that, you also have a stronger tendency to be surprised when what you think should happen doesn't happen. And that's a very strong correlation between those two. So if you're committed into, I know that this is going to happen and it doesn't, you become really much surprised, pupils dilate a lot. And there are individual differences in this, so we can measure this, and that's the correlation. It's a strong correlation. At 6 months, at 10 months, let's focus on 6-month-olds as an example. Now, babies that are 6 months old and are very surprised because what they thought would happen didn't happen. If we take a break for 2 years and ask them to come back to the lab, 2.5 years in some cases, we've done this in several studies, so they're now 2.5 or 3 years of age. We ask them to come back to the lab, and we ask them to do much more complicated social tasks. These social tasks could involve, for example, pro-social actions where they're asked to help and clean up a messy situation that they created. Actually, we're just playing in the room until it's complete chaos with a 3-year-old or 2.5-year-old, and they say, let's clean up. And then the kids goes, yeah, let's clean up. And everything's cleaned up and everything's going to be put in a box. But at the end of this experiment, the child is here, and there always happens to be one toy left here. So the experimenter who sits over here goes, can I have that one? Now previously, they were going in the box, right? Almost all kids help, but about half of the kids put it in the box. The other half of the kids go, wait, no new rules. The person, my friend, requested to have it. And those kids that give it to the experimenter were those that 2 years earlier had a larger pupil than other kids. So we can see this longitudinal trajectory between helping and prosociality at 2.5, 3 years, and these pupillary surprise reactions at 6 months that are related to motor development. We can also see other things where these at 2.5 to 3 years of age, they're also much more, they're listening to, I shouldn't say subtle, but things that relate to inhibition. So many people know of the marshmallow test. You want 1 marshmallow now or 5 later, and it's supposed to be better to take 5 marshmallows later. It can be discussed, but that's the logic of that test. We can't give marshmallows to babies because it has sugar and, So instead we have a glittery wand, which is like even better. It's a wand with liquid and glitter, and you turn it and glitter falls down. It's amazing. So we go to kids, wow, look at this. And it is true, we're not lying because it is beautiful. We put it in front of them and they go and go, please don't take it. Okay, they all take it. But some kids go like, I'll take it anyway. But there's a pause, they're slightly delayed. And then a few kids go, yes, sir, I'm not going to take that one. But then they are like a minority. I would take it, my kids took it, but there are some kids who just wait a little bit longer. And those kids that wait a little bit longer and do not act are the ones that will have the pupil dilation at 6 months. So what I'm arguing here, and I'm going to stop this example soon, but that it's not only important for babies, but this being able to act and interact means that you can predict and form hypotheses about the world. You can learn from when you're wrong. We don't learn when we're right. It's useless to be right. Okay, it's good to be right, once in a while. But from a learning perspective, being right is not an optimal situation. We want to be wrong, because that's when we're wrong we can update and learn, if learning is what we're after. Right? And this is what these kids do, as I see. This prediction and reaction, a surprise reaction, is a beautiful non-verbal way of hypothesizing about the world. You don't need to go, I think this is going to happen because blah, 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 blah. You just look there because that's what's simulated in your brain. And when that's wrong, you become surprised, but you need to update your system. And we can see that, but from 6 months until 24 months, in a singular case, what happens is that the evidence we see is that first the motor behavior becomes important. Then once that is established, they become very sensitive to what I said was not the case, but over time it is. The statistical structure, the repetitions, how many things, sums of things have happened repeatedly over time, that does sit into and become important for their assumptions. And then a few months later, culture becomes important, like the larger socioeconomic, or the cultural environment around you. So it is that the babies can learn from those things as well, but the fundamental first capacity comes from acting. This is when I completely lost track of time, so I have a bit more time. Okay. That was one example. It wasn't one example, but it was one sort of theme. The plan was to talk about different things. Because it's of course not the case when we talk about how hands shape the mind. This is not like the singular phenomena. This is one way in which babies try to start to decipher the world through their own actions. And there are, of course, many other ways. Another way is just when you act and reach and learn to grasp, and it's the same when kids crawl or walk, or we also do it in different ways. But like one important for a baby, first, I shouldn't say the first, I'm going to say the second way that they can start to manipulate the world is again when they can start to grasp for things. So when a baby can start to grasp for things between 4 and 6 months of age, when they feel the weight of things, they see the number of, they get the sense of the tactile structure of objects, how many edges, you get the point. Like they have toys or things that have different properties. And all of those things are like nourishment for the brain. And when I say this is not the first way to manipulate the world, because a newborn that cries, they're manipulating the world. They're changing the environment around them. So they can do that from the beginning. But just that sort of active exploration of starting to take things and put it in the mouth and work with objects and materials seems to also be something that really facilitates cognition. So, yeah, I'm just going to give one example of this, but in a study that we did a few years ago, and we're following it, this is an active intervention studies that we've done in Sweden. We're now doing it in Paraguay with low socioeconomic families that have limited access to education. But in Sweden, what we did is that babies came to our lab with their parents when they were 8 months. And then we did like a baseline assessment of their spatial abilities and also basic mathematical principles like approximate number system and things like that. But let's stick with geometry at the beginning. So we measure how they understand angles and shapes, basically. And kids vary, but they understand this, and basically if you have a lot of angles like this on the screen and one is slightly different from the others, they can pick it up, but it takes some time for them to encode and unpack this information. So we're interested in when they focus on the right one, the one that deviates. So, and then once we've done this pre-test, we give the parents a lot of blocks. These blocks have different colors, shapes, weights, textures, all these things. And then we give the parents an absolutely ridiculous task. We say, go home 5 days per week for 8 weeks, play with these toys together with your baby. Here is an instruction book. When they open up the first page, it says, build a castle with your 8-month-old baby. The next page, build a forest. You can't build a castle with an 8-month-old baby with blocks. It's impossible, but that's the point. Okay? So what some parents just understand this and do this naturally, but those that are a bit reluctant to play with such young baby, they love these books. Put this, it's like a Lego instruction. Okay. But so they start building, and what the kids do that is this. And that's where we're after, that's where we want to be. So what happens then is that all of a sudden these babies have blocks that they can put in their mouth again and touch and feel and interact with. And if 5 minutes per day, 5 days per week for 2 months, then they come back to the lab. And what we can see that those that had that tactile experience of these objects, this active exploration that was guided by them, but actually gave them something, we argue, they had developed much better spatial capacity. So this task that we do in that, they have been much improved in this. Now, as I said, this is an active control study, so we have another group. And there we do something else. They come into the lab, we do the pre-tests, and then we give them another task, which is probably actually for like infant cognition, the best task ever. They're asked to read for their babies. So you should, if you have an 8-month-old baby, read to them. It does wonders for their vocabulary and many other things. Reading is not putting up your favorite big, whatever, and start from sentence 1. But just, you have a book and you look at what the baby is interested in. Maybe it's the corner of the book, maybe it's a color, maybe they want to chew on the edge of the book. You don't even need a book, actually. You can just walk around with your child on your arm, being sensitive to, oh yeah, you're interested in that, that's a lap. Just talking about stuff together with your child. It's super. But in this particular experiment, it's not helping. So it helps for everything except this. So in this case, we had a book which just didn't have the shapes and angles and color. It was a boring book about something else altogether. And the idea is that they should at least spend as much time with their children and they should do meaningful things together. So we should support parenting in the same degree. But when they come back to the lab after these 2 months, they had also improved because, development, but not at all to the same degree. So the active exploration and active, the exploration of the babies helped them make sense of the world and allowed them to develop these spatial capacities much better. And it's the same we would expect with crawling or walking or anything. The third example that I'm going to give, so that was the active exploration part. The third part I'm going to talk about is going back to this marshmallow test. So it turns out that being able to act on the world is not only good for understanding other people and sort of exploring the world, but it also involves very fundamental properties that has to do with planning. So like I said, already in the womb, there is this planning of how one is moving related to future goals. Now if we move up again to babies that are sort of 18 months or 14 months, but during the second year, we can see in their motor behavior a much more advanced type of planning, where babies already plan multiple steps. So for example, if they grasp for something with the intent to later throw it, they're going to move much faster already, like in the first 200 milliseconds of the movement, than if they intend to grasp an object to later put it carefully somewhere. So, and there's been many studies by us and others on this topic, showing that there are multiple step planning happening in the minds of the baby already during the second year of life. Now, that is another form of future orientation, right? But it's a future orientation with respect to your own actions. And what we and others have been arguing is that this planning that babies do at that age is the start of something that is that's a greater form of planning. And we can see, if you look at the neural development of young children, if you think about what's called executive functions, which is the marshmallow test, but it's also things about thinking, planning long-term, again, inhibiting urgent responses for something that is valuable in the long run for you. It's a bit more complicated, but it also involves sort of selection and planning in different ways. And it's good stuff. If there's any correlations that psychology has provided, developmental psychology, is that executive functions are good. And being able to plan ahead and inhibit urgent responses now for something that's better later is like super good. Yes, we all know that, I think, so I don't need to elaborate on that. And in the actions of these babies, there are already this multiple step long-term planning. And I was going to say it, but I dropped myself. But when we look at, I mean, not we, but when others have looked at the neural networks that are involved in long-term executive functions planning, so we can see that early in life, it's a very broad distributed network that goes over the entire brain pretty much and focuses a lot on the motor system and the emerging prefrontal cortex. And then over time, there are two types of planning that network differentiates into two. One that has a really prefrontal center that is really about this long-term planning, about life. And the other one is motor planning. But at the earliest stage, it seems that those are merged into one before they differentiate. And what we and others have shown is that there is a very strong association between when babies start to plan long-term in their actions and their ability to handle executive functions tasks. And we've shown this during the second year of life, and others have done amazing studies when they show that when babies start to crawl during their, so that around 1 year, it varies, but when babies start to crawl, is predictive of the executive functions parts of the brain in 30-year-olds. And we haven't been able to show that, but we can show the same way that in the moment, the children that have good planning ability also have good ability to plan ahead in an executive functions way, to inhibit reaching for the glittery wand, and even solve tasks like you put one, not marshmallow, maybe a racing or something boring, in 1 out of 4 boxes. You spin the box around so you can't really see it anymore, and then you stop it and say, please reach for that one thing. And those that are really good at that working memory task also has this very good motor planning. So I think all of these, I hope, are examples of how important motor behavior is early in life for many different capacities that young children have and that they develop. And that's not to say that other parts of a child's life is not important. So I'm not trying to say that we should all focus on training motor behaviors of babies and ignore the social world around the babies. But I have a few more minutes for this. It turns out that the very things I talked about now, most babies learn. And it's a system that's very flexible. So we can see, for example, if someone is born with limited movement in their arms or absence of arms, people usually use their feet instead to manipulate objects. And that is used that's the motor plan that individual is using to achieve a goal. And that is being used when they see someone acting with hands, for example. So this is something that is so fundamental that the vast majority of us develop it, all of us. So this is not the question about babies that mature early motorically are going to be way better later in life, in psychological terms. It's rather that this is a fundamental principle of how we all learn to organize our cognition through active exploration and interaction. And we all achieve it to a large extent, but it's still that we can sort of, when we look at early infancy, we can still sort of catch it in the moment, and then we see that these associations are very strong. There is some component that if you have very poor motor abilities, you go into in adulthood, we can measure that psychologically, but you have so many compensatory mechanisms that I wouldn't be concerned about some of this. What we instead have seen, so if we want to intervene and support childhood, we need to support active exploration and curiosity-driven learning for sure, that we know. But the one thing that we see that we can intervene, and that is not the focus of this talk, because this has to do with this, is the quality of the social interaction with parents. That is less important at the very, very beginning in order to structure cognition, but it very quickly becomes the most important area a few months after what I talked about when it comes to like the very first months where hands and actions really provide the foundation to decode the social information. But over time, we have also seen in studies after studies that if you have, for example, if you want to achieve a change in a child, the best is to work with a parent-child interaction. And particularly what we focused on in quite different topics, but it relates to this again, is if you have a parent who suffers from mental health, or you have parents that are not present, or that's when children become older, that's where we see the real effect on child development. So I think we need to sort of divide this into two parts. The fundamental starting blocks for all of us lies in motor behavior, I should ask, is my suggestion. But if we want to create change, the most effective way is to utilize the effect of that motor activity, and that's through social. And I wanted to sort of end by emphasizing that, because otherwise there's a risk that what I'm communicating is wrong. Like it's ignore the social and go and make sure that your baby can reach for stuff, and that's not the point, right? So on a philosophical level, hands do shape the mind. But if we want to make and create real change, we need to take care of our babies as parents and siblings, friends in general. Thank you.
So much. So we have questions, comments. Any questions?
I have a question in relation with, okay, let's say, there's a quite popular assumption that, for example, if a kid plays a musical instrument at school, it helps with their, also motor functions. Can it be the same as the same thing happening, or it's too late at the age of school?
I don't think it's too late in school, and to some extent this exists throughout life, right? So this is what I talked about when we did the TMS study with me and the dental chair. You can still see the effects of these things. So I think it's still there, but I do think that the effect of this diminishes over time, because there are so many compensatory layers, more complex layers of understanding other people in the world that are built on top of this. So the marginal effect of this decreases over time. That's what and that is, I think that from people that comes from sort of an embodied cognition perspective, where I'm also starting from, often sort of lack that assumption. I think so it's sort of, we need to train motor behavior all along, and that's just going to be great. But I think that it is a fundamental key to deconstructing the world at an early age. And then that exists, and there are studies actually showing, people that are 80 or older that have diminished motor capacities, we can measure a diminished social capacity in those. But that's mostly on an experimental level. So if you think about it on a more functional level of an individual in their environment, then you have so many other layers of memory and theory of mind and other types of sort of cognitive and social capacities that sort of overcome this. So I think it's great to play instruments, but I do think that also to a large degree practices things like attention it practices memory, it practices a lot of things that are really, really good. But maybe this motor loop, and maybe to me, is something that is essential at the start.
I enjoyed very much your banana experiment. I mean, the speech was generally brilliant, thank you. But I was thinking pretty much on that banana part, which is that kind of introduction. What you told was kind of personal experience, which is perceived to be as something general or widespread. But on the other hand, you gave some examples where this meaning is, I would say, situationally constructed, or whatever you call it. Can children grasp this situationally constructed meaning of something? And if yes, how it happens? Because, I mean, when we grow up, we have to consider that our perception of the world might not be universal. It's personal, and we have to switch between those meanings, my personal meaning and the meaning of someone else. It's kind of switching between perspectives, if you wish. And well, could you?
I think that's a very good call. No, I don't think they're switching perspectives.
But
I think that there are two, and this is the negative part of not having a PowerPoint. There are two things, but I can add two things to this if there's time. One is that when we do this type of studies in different cultures, we see that babies are sensitive to different things depending on what is prominent in that culture. So if you would do this in China, we have actually done this in China, it doesn't work like this. Then there needs to be chopsticks and there needs to be another type of, otherwise it breaks down. But I think the point is that they always, before they have this theory of mind or this perspective taking, they're really just internalizing this as this is how would I respond to this? We narrowed, there's the final thing, but I talked so long about that study, so I sort of realized I had to move on. But the actual coolest thing about the study I didn't tell you, so I'll tell you. I said that one of these actions were normal and the other one was considered just weird by parents. So there is a risk that baby just goes, I've never seen this before, and becomes surprised. And that's a bit trivial. So what we've done is further experiments where it's the same action again. The spoon always goes to the back of the hand, so it's always this weird action. But we place a barrier, it's the same video, we just insert a barrier that looks like a real barrier with shadows and stuff, but it wasn't there when we recorded it. It's either up here or it's down here. And when it's up here, it's sort of irrelevant. And we don't point to it, we don't show that it's solid, it's just there. And then we get the same pupil dilation in those periods. In another condition, same babies or different babies in different studies, we just lower the barrier. So if you think about it, it now sort of becomes a little bit hard to do that action. It's not impossible, but it's just inconvenient. And again, we don't bump into it. It's just there. The food goes back to the hand. It's just a wooden plank like this. And then the pupil dilation no longer exists. And that's actually, to me, that's just crazy. So that means that a 4-month-old baby looks at this and goes, well, given this condition of these two people and the plank, I would say that this is sort of now rational. That's why they put it on the back of the hand, because there's, this would be weird. And how are we able to compute that? I have no idea. I wish I knew, because that's like the bit that when I refer to a big question mark, this is the big question mark. And then you could have a discussion whether this is sort of something that's innate or not. And I don't think it is, but it is really advanced. And we thought for a long time we had some artifacts that has to do with light and pupil dilation. We're pretty sure it's like we've done this with so many different conditions and stimulus, and we feel just confused. I don't know if it answered the question, but I guess I'm confused.
It gave direction.
You described some very interesting experiments, but I was thinking, what next? For example, in physics, you make some experiments, then you develop equations which describe in general the process, and it helps. What about your field of experience?
Yeah, that's a very good point. So we're taking this in several directions. One thing we do, as was mentioned, is we try to understand this in different cultural contexts to more understand variability. That is one thing. The other thing is that we, like the first part I talked about, there's now 50 studies and we've done meta-analysis on it and it seems to be very solid. There, I think we also understand that this on a mechanistic level. So actually, that's the one area where I'm sort of packing this up and moving on a little bit. Because I think if we know the neural structures for it, we know how it works, it's less to be explored. I think for these other two, when it comes to the active exploration and how this relates to more long-term planning, that's where there are more unknowns. And that's where we're trying to do more studies replicating this in different contexts, with different larger samples, and really trying to understand the mechanistic level of this and the cost of structure of this. So that's what we're doing. But, and there are actually models, computational models that can explain fairly much the first part of this. So I think we're you should never be content, but I think that part, I think, given this, the lost unknown, which, in physics, the lost unknown is always the thing that turns things around completely, but I just don't know how to move forward yet. So I'll wait for until someone gives me a brilliant idea.
I have a question. In my mind, when you talked about the whole banana experiment, I think everybody's thinking about the banana experiment. Is the fact that maybe babies make sense of conservation of energy, because when you put it on top of the hand, does it make sense to go there? Because the most effective way of feeding something to someone is a straight line, not a three-pointed line, which goes from the banana to the hand, from the hand to the mouth. It just doesn't make sense, and that wouldn't make sense even if you probably did it to a person who was 20, 30, 50. They would also look at the same experiment and at least be surprised by the action, because you're expecting that same action, and is I don't know where the question is really, but
No, I see it.
Right.
And to some extent, I completely agree.
Mm-hmm.
So when I talked about rationality, what you said is, I think you described it in a very different way, but it's the same thing.
Right.
So they have an assumption that it should be energy efficient,
Right.
or rational, or simple, or whatever term you want to use. But the fact that they have that so early, and that they have that in relationship to the environment, that they can look at the environment and go, well, this barrier, now I understand, now this is efficient, or now this is the required level of energy being put into this in order to achieve this, given the constraints on the environment. That's still a heavy computation, I think. So, but I agree with that's exactly that's the assumption that we have. And that assumption still means that they look at this from the beginning. They look at these two individuals and go, I think this is going to happen, because this is the most efficient way to achieving the thing that they're doing. That requires for 4-month-olds to understand the overall goal. This is feeding. This is what efficient feeding would be in this situation. These are the environmental constraints that lead to the fact that this straight line doesn't make sense. So I completely agree, but I still can't understand it.
First of all, thank you very much for your presentation. It was just wonderful. And for involving the audience. I have never been in such a big 1-year-old auditorium. So it was brilliant in convincing us that we can say as a 1-year-olds. My question is from a bit another sphere, not a banana trial. What are your personal thoughts or feelings on digital devices' impact on child's development? They are using their hands very fast and seemingly effective. How does it impact their mind development, or doesn't?
That's a super good question. I think that the field is sort of starting to come out with good studies. So, what the studies have shown, it aligns well, I think, with the banana example, which, by the way, I've done this without banana sense. But we skip the banana. So what that study, I think, showed also is that even if you show this repetitively 24 times, they don't sort of integrate it. They don't take that information and learn from it. And studies have shown that babies and young children can learn from digital media. but it always, their learning is underperforming with respect to what happens if just an adult sits next to them and go, let's watch this together, or let's explore the world together, or let's have real materials that you work with. So there is either zero or some learning happening, but it's not efficient, it is not good, it's not deep enough. And I think one thing that is essential, if we step away from my experience and talk about digital media, is that we know that learning is always contextual. You need to, when you learn something, you need to integrate it into broader networks in the mind representing things. And when you sit with these things, you just do this task, and you might be able to solve this task very well, but it doesn't generalize to anything. Now, my kids are old now, but they went to school and started learning math when these apps were coming. And I know that they could do multiplication like, on the app. And then I just said, take down the app and says, what's 6 times 4? They go, because, you learn the game and the ecology of the game. You can be super good at this, but it doesn't generalize, it's useless. So I think that a lot of the research that exists, and it goes in line with this as well, that yes, you can learn, but don't do it. That is not where it happens. We need real people, we need interactions, we need context, we need real materials, and that's what we're sort of built for, and that's where learning occurs. I think that's
There is just a question in regards to the banana. You mentioned the embodied mind perspective. I've seen this beautiful video of these wooden mechanistic legs, that seem to fall down the stairs, but each leg is going like this,
Yeah, so the Zurich robot, or
it's something like that. And I was wondering, there's no cognition needed for that process to be, done. And perhaps, in regards to small children, there's this, I guess, embodied sense of, as a colleague in front said, of this, energy conservation. And then you have this prediction error, right? Which is this different way of feeding, which makes you, change the model, adapt the model. Because perhaps there's no cognition, heavy cognition required at the base, because it's just a mechanistic.
Well, I see your point, and I think that the first time I saw that video, I forgot the name. Never mind the guy who made that robot. So it's a slant like this, and they have a robot that looks like a human. It's just made of a few joints basically, and when they release it, it sort of goes like this actually down that thing, and it looks like it's walking. So that's to show that there is an energy efficient way of walking, and that's also an argument why we all tend to walk the same way. We use our legs in a similar way if the legs function as they do for most people. So I think that's an argument for that. But when we look at a young child learning to walk, that is the furthest away you can come from that robot. Because learning to walk is the most painful thing ever. Studies that have been showing that when a baby starts to crawl, or can crawl efficiently, and stand up and start to walk, actually their speed of locomotion decreases. And they fall on average 50 times per hour. It hurts to start to walk. So it's all about trying, the mental strain of learning to stand and walk is enormous. It's all about the prediction error. And that's why it's completely different from that robot. But once you've been able to manage it, it is an automatic process. And then we rely very much on the biomechanics of our body. And that's also why these things, even though we have early in development, vast different ways. There's so many ways to crawl, there's so many ways to start to walk, but we all converge on something that's very similar, which is efficient walking, which is related to the constraints of our body, which is energy conservation and same principle. But the path there is so hard. And that's why there is this development of the mind when it comes to reaching and grasping and walking and crawling, because that is it requires the full attention. And it requires computations that are so intense that the brain gets matured. It needs that. That's is that?
Yeah.
Okay. Thank you so much. Thanks a lot to our speaker again. It was really, really wonderful. Thanks a lot for questions. And now, before we are going to enjoy some coffee and snacks, we have some tradition. Well, many thanks, Gustav, for coming over. And so this is the animal
Here is the card.
That's beautiful.
Thank you.
So, thank you so much. Thank you.
And I pillaged the gift shop of the museum, so some stuff for us. Jason.
Okay, so now it's time for coffee and snacks and discussions about banana experiments.